In the last section, we defined what the definite integral is using the Riemann sum formula. Riemann sum formula was basically calculating the area under the curve using the rectangles, if you remember. But we said that calculating the area using the Riemann sum, right, is so hard job. So we can't use that formula at any time when you are given the right, even when you are given the function itself, finding the area under the curve is one of the hardest problem of the calculus. That's why we need to give a better, okay, and then a fundamental way to calculate what that definite integral is. Today's job is gonna be, okay, this, which is called the fundamental theorem of calculus, and really it is a fundamental and then the most important theorem of the, okay, all calculus. Why it is so fundamental? After looking at this theorem, okay, we will explain more. Look at this theorem, what it says. It says if you would like to calculate the integral, right here, as you see, right, on the left-hand side, this integral will be equal to, right, a big F function. And then the big F and F function value of the, right, the endpoints, as you see. It seems so simple, right? But we need to ask this question, who is the big F? Look at that. The answer is in the, right, the first sentence. It says the big F is the antiderivative of F. I hope you remember, right? Since we solved a lot of, right, antiderivative question, the antiderivative way was this one. So the derivative of, right, the big F should give you the F, and then if we satisfy this equality, this relationship, we said that the integral of the indefinite integral, if you remember, the indefinite integral of F would be equal to, right, the antiderivative of small f. So that is how we, right, define the antiderivative and then indefinite integral. But look at this theorem says if you would like to find out the definite integral, there is a way using the antiderivative as well. Okay, it is so interesting result. Of course, we are not going to get into the proof, but that is the one of the, right, the best thing we can encounter in calculus. Since if I would like to calculate the area problems, right, as you see area problems, it is not just the area of the, right, the curve. It can correspond to different type of, right, the problem in real world applications. And then that is how I'm going to be using the antiderivative to calculate the, right, the area problem under the curve. That is why it is so fundamental. Look at that. This theorem, okay, will connect, right, the derivative by integral. Okay, that is why, okay, it is so fundamental, it is so basic, it is so important, and it gives us a way, okay, how you need to figure out this integral result. It says just find out the antiderivative and then evaluate the endpoints under that function. But as you know, finding the antiderivative could be, right, some tedious job. That is why we saw the substitution techniques and some other, right, the integration techniques like the power rule, like the other features, and then we use them to solve the antiderivative problem, which is of course solving definite or the indefinite problem from now on. So now I'm going to show you a couple different examples so that we can see how I could apply this theorem, okay, to figure out the definite integral or area under the curve problem. Let's solve a couple examples. So 1 to the 2 x squared minus 3 dx. So as you see, this could be seen as an area problem under the curve, right? Since the curve of this function is this one, x squared minus 3 is something like that. This is the curve I'm talking about. But I just wanna, let's look at this example. So basically we are being asked, right, the integral of x squared plus 1 function between, right, these numbers. As we know, right, this is the area problem under this curve. This is the curve corresponding to this function, and I would like to calculate the area in this interval. So what I'm gonna do basically, I need to find out, right, the antiderivative of this function and then figure out the value under that antiderivative. How am I gonna find the antiderivative of this? As you know, I can just use, right, the power rule. Power rule says take the derivative integral in this way, x cubed over 3 plus, right, the derivative integral of the 1 is gonna be equal x. There is not gonna be c, we were adding, right, to the indefinite integral. Previously, since this is the definite integral, if you look at the theorem says you just need to evaluate, right, the antiderivative under these endpoints value. So that is what I'm gonna do. This is my antiderivative function. I figured out, but right, I need to find out the value of that function for f of 2 and then f of 1. So my f of x, as you see here, right, I solved it. It is this one. What I should do, I should find out what the big F of 2 minus, right, what the big F of 1. I need to subtract these values. What is F of 2? F of 2 is equal to 2 cubed over 3 minus, plus 2 minus 1 to the cube over 3 plus 1. So if you calculate this value, okay, that's going to be my end result. So if you calculate this value is going to be equal to 10 over third, which is going to be the area then is equal 10 over third. We can just basically say this result. Before solving some other examples, we're going to need, okay, some other features to calculate the complicated type of functions integrals. So these are the features we are going to be using for that purpose. So look at that. What it says basically if you calculate, right, the f of x times k can be taken out, right? Just ignore and then multiply it later after taking the integral. If you are adding the functions, you can add their integrals, right? Instead of adding first, just later, right? Add them later. And then if you have the same bounds, right, that integral is going to be 0. Since there is no area under that curve, there is no curve since it's just 1 point. So the integral can be split up, okay, between the value, look at that, for any real number c, but the c is going to be, okay, between this interval, guys. So if the c is between, okay, this interval, you can just calculate this integral by splitting up in two different integrals. And then you can just reverse the endpoints, okay, by just multiplying the negative. If you want like to, okay, switch the endpoints, you just need to multiply by negative. So let me give you one more example so that we can use some of these features to solve the integral. As you see here, I try to add, right, 3x with the 5 ln x. If I use the features we just learned, I can split this up, right, into two different integrals since I'm just adding them. Look at that. 3x is going to be one of my integral, right? 5 ln x is going to be other integral. And then also look at that I can take out these, right, the constant, since the effect can be seen later instead of seeing them, okay, first. Look at that. I'm just going to take them out and I'm going to multiply later. So now I can, right, take the integral of what the x is. So if I use the power rule, that's going to be my integral, right? X squared over 2 and then just the 3 and then endpoints. This is my antiderivative as you know now. 5 times, what is the antiderivative of ln x, right? Let's look at this example. As you see, I'm just adding a polynomial by an exponential function. I can't just integrate at the same time. I don't want to integrate at the same time. I want to use the features. So that is how I'm going to be using. I can split this up right into the integral, which is going to be 3x 1 to the 2 dx plus 1 to the 2 5e to the 2x dx. So, and also I can use, right, a constant multiple feature, which I can just take this out, right? Let me do that. 3 could be written in this way, and then 5 could be written in this way. So now it is time to figure out each function integral, right, alone. So what is the integral of x using the power rule, which is going to be equal x squared over 2, 1 to the 2, and then 3 I have here. And also look at that, the integral of e to the x, you remember, right, from the integration section, e to the 2x over 2. And now look at that, I should be using, right, my endpoints to figure out the entire derivative. So 3 times 2 squared over 2, 2 squared over 2, minus 1 squared over 2, right? I'm just using the endpoints. This is the value when I use x equal 2, and then this is equal x equal 1. This is just for the first integral. And plus I have here, look at that, 5 times e to the 2 times 2 over 2 minus e to the 2 times 1 over 2. And then this is the for the second integral, x equal 2 and then x equal 1 respectively. And then if you calculate all these values, okay, it doesn't matter what value you got, since you need to use the calculator. I'm not going to be using it. You can just leave in this way, of course, okay, it is acceptable. But the idea behind that, right, to take the integral of this problem, we can just write the combine all the features of the integration itself, also taking the entire derivative techniques we learned before, like the power rule, like the substitution, okay, all techniques can be combined to take the integral. Now I'm going to give you a couple real-world example to see, okay, how we can use the definite integral problem to solve the real-world applications. If you had a function, right, like this one, you would figure out all the populations in any country. So this is for the US. The statistician modeled the US population by this function. So if you would like to figure out how many people lives in US, you can just use this function and then take the integral, which it will give you the area under that curve, and then that will corresponds to all the populations lives in that time. In that time, we mean actually from 0 to the 9 decades, which corresponds someone which is at the 90 years old, sorry. So if you calculate this integral, look at that, that will give you the 286 million, which is so correct, right? In these days, actually, we have this many people living in US. If you would like to find out, right, population between any age, right, like in this example, between 4.5 years old and 6.5 years old, 65 years old and 45 years old, these are corresponding, almost these years, since if you subtract these from this, this will correspond to 45 and then 65 years old peoples, and then that many people, between these years lives in US for now. So it basically, gives us all these numbers at any age, which is so useful for a lot of different purposes. So think about, how you could use this type of information if you had such a form. You can also figure out the length of the trees using the area formula if you had a nice function. Of course, always, you need to have a function, you modeled, the problem you have, or you need to have some data, as we did before, using the Riemann sum. So if you have the model like this one, look at that, this is the model for the rate, the tree growth. So you can basically determine the length of the tree at any year. If you have this formula, I can just take the integral of it using all those features, power rule, and the entire derivative substitution techniques. If you look at if you take the integral of this one, look at it, it's just a constant 0.60, and then if you take the integral of this term, which we use the power rule here, then of course you need to use the 2 as you see here, and then also 1. This is basically x equal 2 values, and then this is x equal 1 values. And look at that, after 2 years, then this tree, eucalyptus tree, will have this length. So the b part is the same, you can just put here the x equal 3, and then x equal 1. You can just calculate the same value similar result for the B part. As you see, the area problem actually corresponds to so many different problems in real world, and then that's how we use the integral OK to figure out the solution to that type of problems, guys.